Greetings, Algebra 2 Trig students. This is 2 for the price of 1, sections 8.4 and 8.5. Common and natural logarithms. So, let us begin. We shall begin with a common logarithm. I have mentioned this to you before. So, what is a common logarithm? It's very straightforward. It is a logarithm with base 10. So I'm going to bring my calc up in a second, but like my favorite I like to do is log 100. I've said that in class. I'm going to do it here in a second. Now remember, when we see log 100 like this, we don't write the 10. So if nothing is written, there really is a 10 here. And if you recall, a logarithm is an exponent, and since our base is 10, the question really is what exponent gives us 100. So we're going to see that in a minute, that log of 100 is equal to 2. Now, I also want to do maybe a yuckier one, so I'm going to write it here and then I'm going to go over my calculator, because we can figure out the log of whatever we want, as long as x is greater than 0, I should say. So let me bring up my calc, and just to review, the log button, if I hit log 100, and it's a bad habit not to close parentheses, so I'm going to go ahead and close mine, and sure enough, there it is. It says that it's 2. So maybe somebody might ask us the log of something else, and you'll see some of these on the problem set. So what's the log of 8? So notice the log of 8 is something yucky, okay? And I'm just going to come right back on over here, and I'm going to write what that yuckiness is. And it's actually an approximation. It is 0 because our calc runs out of spaces. 903089987. So, if you recall, the log of 8 is common log, and in the end, really, there's a 10 there, so 10 to this yucky number will give you an 8, which your brain is never going to be able to tell you what that yucky number is. Which leads me to the next concept, and that is what we call anti-logarithm. I have also mentioned this. And so basically this whole thing about the anti-logarithm, if I have this log 8, this thing sitting in that position really is the anti-logarithm. So the anti-logarithm is basically you're going to do the opposite thing that you did with the logarithm. So if I want to figure out what 10 to that yucky number is, I'll just rewrite it up here again. 0.903089987. What I would do on my calculator is I can hit second log, and you'll notice that second log really is what's going to help me get my anti-logarithm, and sure enough it produces a 10 raised to a power. And now I'm going to go ahead and hit second answer, because that's going to bring that yucky 0.9030 in, and sure enough when I hit enter, what happens is the 8 comes back to me. So to see it maybe in something a little more friendly, let me go ahead and clear my screen here. So if I say I've got the log of 100, which we know, if instead someone says, well, the log of x is 2, what is x? X is what we call the anti-logarithm. So then what I would do is I would hit second log. So I'm just doing the opposite, and I'd put the 2 in, and sure enough what comes back but my 100. So it's just going back and forth between taking the log and figuring out what the log is. Okay, let me just write kind of a baseline thing down. So when we have log with whatever base it may be, x is equal to y, just to give some variables, then we would say that x is the anti-logarithm of y. And if you just remember, you're just sort of toggling back and forth between log and second log, and that will take you back and forth there. So as another example of that, if we get some kind of problem where it says the log of x is equal to 2.8 7, 5, 3, 4, find x to the nearest tenth. This is a situation where we are finding the anti-logarithm, because this thing right here is the anti-logarithm. If it instead said, like, find the log of 2.87534, we would just hit log and put the number in. But since we're looking for this thing in this position, then what we're going to do on our calculator is we're just going to go in here and we're going to hit, I'll just clear this out again, I'm going to hit second log, because I'm trying to find the anti-logarithm, and type in 2.87534, and I'm going to hit enter. And out comes 750.48, blah blah blah. And so in the end, with this problem, since it's asking you to round, it would turn out to be 750.5. Okay, I'm going to do this next example. It's not my favorite, but it does give me a chance to do a little review, so I'm going to go ahead and do it anyway. So it's kind of an odd problem, but say you get this problem and it says use logs and anti-logarithms and anti-logs to find the value of 4.20 cubed times 0.781 all over 4.83. Now normally you probably would just put that in your calculator, calculate it out, and figure out what it is. But since the problem is asking us to use logs and anti-logs, I'm going to go ahead and do that. So how would I do that? Well, what I'm going to do is I am going to take the log of this 4.20 cubed times 0.781 all over 4.83. But I'm going to go ahead and I'm going to apply the rules that we've learned, because I can break this whole thing into pieces, and I think this is a good opportunity to review that. So in the end then, what I have here is I have the log of 4.20 cubed, which I would normally write the cubed up here, but if you remember from our power rule, the 3 can come down in the front of this. When I have multiplication and I'm writing this out, I'm going to write plus the log of 0.781. And then division, if I'm breaking it out, turns into subtraction, which is log of 4.83. So I could go over to my calc and do this for you, but instead I think what I'm going to do is just tell you what the value is. You can check it on your own calculator. So if I do that all out, I get 1.078451774. Now, where does this whole anti-log come in? Well, basically by taking the logarithm of this stuff, I get this number. But now what I need to do is take my anti-log. So I'm going to go ahead and I'm going to go in reverse, because I want to say, okay, if the logarithm is this value, so I would hit second log and type this in. And if you recall, this is going to produce a 10. And then I'm going to type this into this position. Then I will find out what this right up here is equal to. So I'm going to come on over to my calculator and do that. So if I hit second log, notice I get the 10 served up with the exponent, and I'm going to go ahead and type in 1.078451774 and hit enter. And out comes 11.979, etc. And it's asking me to round to the nearest tenth. So when I look here at the tenths position, I see that 7. I'm going to round up to 12.0. Okay, so once again, I think this is not the best problem, but it gives you sort of an opportunity to review these laws that we've learned. And I'm going to just do the quick review of them right now, so if you want, you can write them down. If you recalled, what we learned was that the law of a product, A times B, is exactly the same as the sum of the logs of the factors. We also learned that the log of a quotient, A over B, is equal to, written as a fraction, I'm just going to say it's the log of the numerator minus the log of the denominator. And then the last one is if I have the log of a power, that's exactly the same as b times log a, as the power times the log. So those are something that should come in handy. Okay, last thing I want to talk about then is what we call the natural logarithm. And basically, unlike the common logarithm whose base is 10, a natural logarithm is a logarithm with base e. And we met this back in the last chapter, e. So, same thing, we can just hit ln on our calculator. So this is one thing we do need to know, is that natural log is shown with ln as opposed to log. So if you hit the ln button on your calculator and type in a number, so I'll go ahead and hit ln of 8. So the ln button is right below the log button, and I'm going to hit ln of 8, and out comes a yucky decimal. Now, to toggle back and forth, if instead I had a problem that said the ln of x is 2.07944, etc. If I then instead hit second ln, you'll notice that the base of e comes out, and I'm going to go ahead and hit second enter. And something weird just happened there. Hold on, I didn't mean to hit that. Hold on a minute. Let me try this again. Okay, if I hit second ln, I get my e, and now I actually hit second with the negative sign. Brings my answer, and I'll get myself back to that 8. So nothing really different except that a common log has a base of 10 and a natural log has a base of e. So in this particular case, we saw that ln of 8 was equal to 2.079441542. And we learned that when we hit the second ln button, instead of a 10 with an exponent coming out, we get an e with the exponent, and if we deposit this value in, we will get our 8 back, or whatever our original ln was. And so ln's come in handy, and we're going to see cases down the road where ln is more handy than a log. So say someone says, hey, what's the ln of 23.75? All you need to do is make sure that your finger hits the right button. So instead of hitting the log button, we want to hit the ln button, and that would be 23.75, and these are as easy as they get, really, and out comes a decimal, 3.16, etc. Okay, just write that down to be complete. 1, 6, 7, 5, and oftentimes you'll be asked to round, but in this particular case we're not. So another type of situation then would be if you're instead told that the ln of x is equal to 2.87534, find x to the nearest tenth. You need to realize that instead of taking the ln of a number, you're looking for the anti-logarithm. So we're going to use that toggling kind of thought process. So instead of hitting ln, we're going to hit second ln, because this is going to have something with a base of e. And then I'm just going to type in 2.87534, and I'm going to hit enter. And out comes 17.731 or 733, etc. And 2.875. Oops, I put the wrong direction from what I had originally planned. Hold on a second. My fingers aren't doing what I want them to do. Okay, 2.87534. Enter, and I get 17.7314, etc. So if I'm asked to round that to the nearest tenths, I would say that x is equal to 17.7. Okay, summary. Common log base 10, ln, natural logs base e. One more example, because you're going to see this in the problem set for these sections. And I've already done one of these in the previous video, but just to review. If log 3 is equal to x, and log 5 is equal to y, find the following in terms of X and Y. And I have to tell you that these are quite popular on the Regents because it's forcing you to show some understanding. So, say I'm given log 27. Basically, with problems like this, you got to figure out what you can do to get yourselves into having a log 3 or a log 5 so you can substitute your X and Y. So, sometimes it might take a few tries to kind of figure out what to do, but in this case, 27's become pretty familiar to you, hopefully, as also being equal to 3 cubed. And using the rules that we've learned, then I can rewrite this as 3 log 3. And then I can come over here and say, oh, what do you know, log 3 is equal to x, so then I can write that as 3x and be done. And one more example. Say you ever given log 3/5, same directions. Your job is to write this in terms of x and y. So using the rules that we've learned, I can rewrite that as log 3 minus log 5, and then I can look up above and say, hey, wait a minute, log 3, they want me to call it x, okay, minus log 5, they want me to call it y. So I've done what I've been asked to do. Okay, that is it for the 2-for-1 special, 8-4 and 8-5. So you should now go to mathexcelforschools.com and do the quiz.